this computer. Okay, so we start the recording already, and today we are going to talk about the heat transfer in the internal combustion engines, right? Because we already talk about the combustions, we already talk about the cycles. So in terms of improving the efficiency or the performance of the engines, we have to find out how or and where the heat is transferred throughout the internal combustion engines, right? Okay, so let's first look at the energy distributions, right? The energy distributions. Okay, so the input come out from the heat, right? So the amount of heat, right, that is available for use in the engine come out from the mass flow rate of the fuels, right, time with the heating value or the calorific value of the fuel. So this is the amount of the input heat, and this amount of heat will be distributed throughout the internal combustion engines, right? So the first one is this heat will convert into the brake work rate or the brake output rate, right? Using what? Using the brake thermal efficiency. So the first amount go to the brake work rate. And how do we know? We know it from the brake thermal efficiency and also the combustion efficiency, right? So the brake work rate, right, come out from the heat that we give or input to the engines time with the combustion efficiency because we have to combust the fuel, and then this amount of heat is converted, right? How good that this amount of heat convert into the brake work rate depend on how much that we can get from the brake thermal efficiency. Okay, so this picture gives you the overall where the heat is transferred through. Okay, so in here we show you the percentage of intake fuel energies, right, versus the speed of the engine. Right? So the amount that we mentioned vary according to the engine speed. Okay, so you can see that the bottom line here, the line on the bottom, is the brake powers, right? So the brake power vary according to the engine speed, right? And then above the brake power line, you see the coolant load line, right? This is where the heat transfer to, right, to the coolants that circulate within the engine. Okay, and then the next slide show you the exhaust enthalpy. So this is another heat that go out with the exhaust. Okay, and then we have the heat that is lost to the surroundings, right? Throughout the surroundings, right? No using, no using the mass such as the coolants or the exhaust, right? It can go out by itself via convection heat transfer, right? So this is the amount of heat loss to the surrounding, right, without using any mass as a media to transfer the heat. That is different from the coolant load here and the exhaust enthalpy here. And the last one is the friction loss. Friction loss, right? So in all here, right, if we sum all of the each amount here all together, right, you will be surprised that wow, if you sum everything all together, it shows more than 100%. Right? Don't be surprised on this because this what happened is they repeated the count. The count that they repeat on the energies is on the frictions, right? The friction losses that show here, which is about 10%, right? It is the mechanical loss in which only one part of the frictions is converted from heat. So the amount of heat that we input, right, go out, some of it go out in terms of frictions, right? So frictions consists of the contribution from the heat that we input. And when the engine have the motions, there's another friction come in, right? So the less of the friction loss, not including from the heat, convert from the mechanical motions within the engines, right? So you can see the repeated energy in here in friction losses, right? Because original one come out from the heat, right? And that original one turn into friction at the very beginning, right? And then the part is moving, the parts move inside the engine, and due to that motions, another friction come out. This is from mechanical motions, not from the heat, because the heat already finished, right? The heat that turn out into the brake power and give you the motions already done. Okay, so the friction that show above here, they take into account for both the heat and the mechanical motions, right? So the total percentage that show here is more than 100 because of this, right? And when you look on this side, right, you see the amount of each part in here, right? For the brake power, it will take about 20 to 30%, right? And then coolant take about 50 to 35%, right? Depend on the engine speed, okay? And then for the exhaust, right, higher engine speed, you have more loss on the exhaust enthalpy, right? This is different from the coolant load, in which for higher speed, this loss to the coolant is getting lesser, okay? And friction go with the speed, same as the heat loss to the surroundings, okay? So this gives you the picture where the heat that we input to the engine go after it's getting into the engine or into the cycles. Okay, okay. So in overall, we look at what is the power that we generated from the rate of the heat input. Right? We have the brake output of the crankshaft, right? That is the W dot shaft here. This is the useful work for us. We have the rate of heat transfer loss to the exhaust. We have all other losses, or other rates of heat transfer loss to the surrounding by the heat transfer, right? And also we have the powers, right? We have to contribute some of the power to run the engine accessory, right? So if we look at this kind of pictures, right, the shaft work that we receive will be 20 to 40%, right? In which for the CI engine, the number go usually high. For the SI engine, usually go on the low end, the lower end, right? For the exhaust, it's gonna be about 20 to 45, and to the surroundings, right, about 10 to 35% in here. Okay, let's look at in more detail about the rate of heat transfer loss to the surrounding, right? We have what? We have the coolant loss, because later on it have to go out to the surrounding. We have the lubrication oil, right? The heat that transfer to the lubrication oil or the engine oil, right? In which later on it go to the surrounding. Okay, we also have the ambient that directly go to the surrounding at the beginning. Okay, so these are considered all the losses here. Okay, this is what they mean by this definition, by these expressions, right? If they want to take into account of all of the heat that transfer to the coolants, to the surrounding, to the exhaust, all of this considered to be the heat that we cannot use, right? It have to be taken out from the engine. So we can call it in overall the heat loss, okay? So it depends on how you look at, right, how the energy is distributed, right, from the heat throughout the internal combustion engine. Okay, since we have the heat transfer on the engines, look at the impact that the heat transfer have on the engine. Okay, the first one, the impact on the efficiency and on the power, right? The heat transfer that have or happen in the intake manifold, right? If we do have the heat transfer, right, in the intake manifold where our mixtures flow before it getting into the cylinder, right? If we happen to have a heat transfer in these regions, right, it will decrease the volumetric efficiency, right? Because the heat, what happened? Heat get into the intake manifold, flow into the intake manifold, right? So the mixture receive the heat. What happened to the mixture? The density of the mixture decrease. And when the density increase, it means volume getting bigger, right? So with the same amount of mass, right, it occupy more volume because of the density increase, the density decrease, right? Okay, so this is what happened if you have the heat transfer in the intake manifold. Now, if you have also the heat loss in the cylinder wall, right? This heat loss through the cylinder wall is considered to be an exergy loss, right? Why? Why it have to be considered to be an exergy? First, we have to understand the word exergy. This word, not energy, is a exergy. In fact, in thermodynamics, we have one chapter that belongs to this exergy. Right? When we talk about the exergy laws, this is the important laws because this is the law that prevent our engine to reach the maximum allowable work. Right. So if you want to find out why your engine cannot go up to this amount of work as you expect that the engine should deliver this amount of work for you, right? The loss that you have to looking for, right? If you can pinpoint the exergy loss, right? This will help you solve the problem why your engine cannot get more work than you expect. Okay, and his loss to the wall is one that is considered to be an exergy loss here. Okay, so this is the impact of efficiency and power, right? If it happened in the inlet, the volumetric efficiency decrease, right? And if it happened to the wall of the cylinder, right, it's an exergy loss here. Okay, how about the effects on the exhaust temperatures, right? Okay, if we have more loss or less loss about the heat to the exhaust, right? This will affect the turbocharger performance, in which if we have more heat carry with the exhaust, right? That means more heat loss that carry out with the exhaust. It means good. Good for whom? Good for the turbocharger, right? Because the performance of the turbocharger is better on that, right? That is heat loss to the exhaust, right? That affects the turbocharger. If you have the heat transfer more in the cylinders and also in the exhaust system, that you more heat inside the cylinder and then go to more in the exhaust system. This will have impact. Okay, this amount of heat transfer will have impact on the characteristic, no, catalytic catalytic converter performance. Okay, the catalytic converter performance. The catalytic converter is the device that will reduce the emission that come out from the engine. We will talk about this more when in our next lectures, right? So if you have higher heat, right, your performance on the characteristic converter, right, gonna be bad because this equipment could be overheated and will not work properly. Okay, so this is the impact on the exhaust. Okay, how about the impact to the frictions? Okay, the heat transfer impact to the friction. Friction due to the heat transfer will govern not only the temperature of liner. Liner is what? Liner is some coating, right, that you have on the cylinder surface, or it may be a sleeve, right, that you place it on the surface of the cylinder. Can be either one of these. Okay, so if you have frictions that happen because of the heat transfer, right, it will control the temperature of the liner, it will control the temperature of the piston and ring, and also the oil, right. This is what the friction do to that. And when it control, it means it will affect the distortions of the piston and ball, right? Because if the piston have high temperatures, it can be deformed, and this deformation we call it a distortions, right? And when distortion happen, right, sound come out, vibration come out, because the clearance is changed. Okay, so friction control this, right? So in other words, we can say that, right, since this friction due to the heat transfer, it creates the thermal loading, right? And this thermal loading that happen because of the temperatures, that happen because of the distortions, it will indirectly determine the power capacity of the fans, right, that blow the cool air to cool down the engines. It affects the oil cooler, the power used for the oil cooler, the power used on the water cooler, and also on the pump. Okay, so this thermal loading that come out because of the friction due to the heat transfer, right, will have the effects on the power of this equipment. Okay, the fourth effect is on the fourth impact is on the component design, right. The amount of heat transfer that is used to determine the operating temperatures of the critical engine components, right. Amount of heat transfer that happen, when you become a design of the component, right, you have to think about the amount of heat, right, because this heat will be used to determine the operating temperatures of your critical engine components, right? And this heat also affects your component durability via the mechanical strength, via the lubricant behavior, and others. So you have to know the amount of heat transfer that will happen and include that into your considerations when you design the engine component. Okay, because of the lifetime of the component gonna be affected by this amount of heat transfer. Okay. Heat transfer also have an impact on the mixture preparation in the SI engine, right? Because in the SI engine, we will mix the air and fuel together first, right? So this amount of heat transfer, right, that transfer to the fuel will significantly affect the fuel evaporations, right? So in terms of that, right, if we have heat transfer to the fuel evaporate, right, and that means fuel have ability to mix with the air, right, in that sense, right. And also the amount of heat transfer, right, will also affect the cold start calibrations due to cold mixture. That means if we have the heat transfer go out from the mixture, right, especially during the winter seasons, right, where the outside temperature is lower, right, so our mixture fall in and then it lost its heat to the surroundings, right, have the heat transfer from the mixture go out to the surrounding because the surrounding temperature is lower. So this cold mixture, when it fall into the cylinder, is gonna affect, right, the start of the engine, right? So that we have to do the calibrations that consider on this amount of heat transfer, right, when we operate the engine in the winter seasons, right? And then we have to do another calibration on our engine when we do operate the same engine on the hot season, because the direction of heat transfer is changed between surrounding and our mixtures. Okay, so this will affect on the mixture preparations for the SI engine here. Number 6 impact is on the cold start of the diesel engines, right? Because diesel engine, we do not have mixture at the very beginning. We have air and fuel flow in separately. Okay, so how the heat affects the cold start of the diesel engine, right? Because right, diesel engine rely on compression ratio, right? And this compression ratio, right, is covered by the cold start requirement. Right? That means if you start your engine during winter season, you want a higher compression ratio, right? You want heat, right, to transfer during compressions, right? Because you need the heat from compressions, right, in order to ignite the engine, right? If you start it in winter seasons, the heat that come out from compression or compression heat, some of it may go out to the surrounding, not all of it go into your cylinder, right? So you will have a problem of starting this engine because of this, right? You do the compress, you expect that the heat that come out because of compression of them should go into the cylinder to help ignite the fuels, and then combustion happen. But instead, some of the heat go out to the surrounding because the surrounding temperature is lower. Okay, so this is how the heat transfer have an impact on the cold start of the diesel engine. Okay, number 7. Okay, heat transfer impact on the SI engine octane requirement. Okay, on the octane requirement, the heat that transfer will influence the inlet temperature of the air mixture, right? If it go in, your inlet air temperature go up. If you go out, your inlet air temperature go down, right? So it affects on this. It also affects on what? Temperature of the combustion chamber, right? The temperature of the combustion chamber, on the temperature of the cylinder head, on the temperature of the liner, the piston, and the valve, right? And that means what? If since it influence on all of this, right, it will determine, it is the one who determines the value of the N-gas or the exhaust temperature, right? What should be the temperature of the exhaust gas, right? Because if the heat transfer to this, to that, to those, to where, to whatever, right, not concentrate on the combustions, right, the N-gas temperature will change, right? And this will affect the NOx, because if you have heat transfer out, right, so less NOx might happen. But if you have less heat transfer out, you keep much of the heat in here. If it's too much, your engine can be knocked on that much of heat transfer. Okay, the heat transfer also affects the deposit, something that left over, right? It won't go out with the exhaust, just left over inside your cylinder, right? And it start to build up, right? And this deposit, right, can absorb the heat and transfer the heat depend on the stroke of your engine, right? Because we have temperature variation. So if inside is high, it will they have heat transfer to the deposit here, it will absorb the heat. But when inside is temperature is low, right, it will release the heat, right? And the way they do that, right, they can dissolve or absorb the hydrocarbon as well, right? And all of this again will have the effects on the engine NOx. This, okay. So in conclusions, right? In conclusion, we have mentioned about the impact of the heat transfer on the engines in several aspects here. right? So in conclusion, the heat transfer is considered to be a very serious problem, right? And it is something that we cannot avoid, right? We have to face it. Right? It happens always, right? Because what? Because we need a high temperature to combust the fuel. Right? Our need on the high temperature forces us that we cannot avoid to have the heat transfer, right? And also because we want to keep the temperatures at a controllable level in order to operate the engine safely, right? We cannot have zero heat transfer, right? And on the other side, we cannot have too much heat transfer. So the amount of heat transfer have to be controlled, right? For the sake of engine operations. Okay, so that is why important for an engine to have a heat removal process. Right? So we have to have a heat removal process, even though we want a high temperatures, we want to keep the temperatures, right? So we have to have the heat removal process, right, to maintain the engine at the safe operating condition. So this is another reason when we build up the engine, not only because, right, in thermodynamics, right, when we talk about the heat remove process or QL, we talk about in terms that for the cycle to exist, it needs heat that transfer out, not only the heat that transfer in. Right? According to Kevin Planck's statement or Clausius statement, that what we know why we have to have heat go out from the cycle. Right? That's what the thermodynamic people say. Right? But in the actual world, right, we need the heat removal process, because if we don't remove the heat, right, nobody can be sure that the engine will operate at the safe operating conditions, right? Because the temperature may get up too high, right? We cannot keep the temperature at the controllable levels, so everything or component of the engine can be damaged, right? It because of this. So it on different aspects when you look at, right? In academically, Kevin Planck's statement, practically, safety reasons. Okay, so that's why we have to think about how we can remove the heat. Right? There are two ways to reduce the temperature in the engines. Right? One, by using the water jacket. That means the circulation part of the water in order to transfer the heat out from the engines. Right? Another way is by using the air. The air that we mean is the air outside, right? That flow pass through the engine, right? So we need to have more area, more surface area on the engine, right? So our engine have to have fins, right? Fin. Okay. Okay. So since we deal a lot with the heat transfer, we know how the heat transfer impact to our engines, right? That force us to study about the heat transfer, right? So to study about the heat transfer, we need to know the heat load characteristic. Right? This is very important. We need to know how our heat load behave. Right? So the first thing that we know is the heat load in the cylinder is very pulsating. That means it's always fluctuating. Right? It never be steady. It's always up and down, up and down. Because of what? Because of the temperature that difference between the combustion gases and the cylinder wall, right? The difference of this temperature, not only because it difference, but also because of the magnitude of the difference that can go higher than what? 2000 Kelvin, right? So this is the source where our heat load is sometimes unpredictable, right? It's up and down in here, right? And second characteristic is that for different pressures in the cylinder, this heat load is also different, right? So it's not only different because it's up and down, right? But for different location, it's also different, right? So we have the heat load vary according to pressures in the cylinder. Number three is that if you think about insulations, right? You want to use insulation in order to control the temperature level, in order to control the amount of heat, right? Instead of using the air, instead of using the water cooling, right? You want to use insulations, right? Number three said it's almost impossible, right? It's almost impossible. Because what? Because your engine will operate in so many conditions, right? So your insulation have to be flexible enough, right? The thickness have to be very in which it that what it means is possible, right? And if you don't use it properly, right, or you try to use the insulation, it may lead to a strong increase in the wall temperature level, right? And also high surface temperature fluctuations, right? The high temperature surface fluctuation happen because we are not operating the engine in only one speed or in one condition. There are several conditions that we operate our engines, right? So the surface temperature can be different or can be fluctuated, right? Because our insulation is fixed on the thickness. Okay. Number four, right? The high temperature gradient in the wall, right? Because we have the heat transfer to the cylinder wall, right? So when we talk about high temperature gradient, it means the different temperature between the inside of the wall and the outside of the wall. This is what we call the temperature gradient, right? And when we say it's high, it means this difference is high, right? The temperature inside the wall and temperature on the outer surface of the wall, the inside surface and the outer surface, right? And these high temperature gradients cause what? High temperature tensions, right? Or in other words, high thermal tension load here, right? Especially in what? In the piston, in the liner, and also in the cylinder head. Okay. Number five, because of this high temperature tension, right? Especially when it happened on the piston, right? We have this high temperature tension occur in the piston, liner, and cylinder head. Number five, talk specifically on the high piston temperature tension. If we have that, right, it occur here because of the oil temperature for the piston cooling cannot exceed 250, right? We have to allow the piston to have high temperature. Somebody think, why don't we keep it down, right? Why don't we keep it down, right? But if we keep it down, right, the oil or the lubrication oil that receive the heat from the piston, right, the temperature of that lubrication oil can go higher than 250 degrees Celsius, right? And what happens if the oil temperature go higher than 250? To make the temperature tension of the piston to go low, right? What happens is these higher temperatures, 250, can cause coking of the oil. That means what? Instead of the oil being a fluid, right, it starts being a solid, or partially of the oil will become solid, right? So no more circulations of the oil, right? So the oil temperature that we use for the coolant is limited on 250 degrees Celsius. cannot go higher, right? So we have to trade off. We cannot intend to have the piston temperature tension to go as low as we want, right? But instead we have to keep it as high as it will not let the oil temperature to go up or beyond 250 degrees Celsius, right? So inside the piston, I show you right here, they have a oil cooling gallery, right? And we have a piston link groove, right, inside the piston, right? So in here, you can see that on the bottom of the piston, we have the oil that is injected, right, into the gallery, and then it flows around inside the piston. Along the way that it flows, it will shaking, right? It will be shaking up and down in the direction of the piston, right? When the piston go up, piston go down, right? And inside here, it look like this, right? That the oil keep going on around, and while it's going, it go up and down as well, right? And then it's go out, right, to the crankcase below, right? And another new oil flow in, and round again, right? So this is what happened in the piston in order to keep the piston temperatures. Okay. Okay. How about the groove? Show right here, right? The former one we show you the gallery. This one I show you the groove, right? Inside the groove, you see the hole, right? We have two holes here. That is called the oil return hole. Oil return hole, right? And that means the oil, when it get into the piston, right, some will go out to the groove, right, using this hole, right? We also have the oil scattering, if you remember, at the bottom of the piston, right? The ring at the bottom of the piston is the ring that used for scraping the oil, right, to go down. Okay, the oil to go down. On this side, you also see the hole here. Okay, see the hole here. So the oil not only come in and out here, but it also come out on the groove here, right? On the groove, show like this. Okay, okay. Since every part of the engine receive the heat transfer, right? And it receive different amount of heat transfer. So the engine temperature is different from presses to presses, right? And in this picture, show you the temperature distribution for an internal combustion engines, right? Where if you look at this picture closely, right, you can see many temperature happen all over the engines, right? But the most serious ones, which is the highest temperatures, right? It happened in here on the spark plug, on the exhaust valve or port, and the piston face, where you can see the temperature is about 300, 600, and 650, right? And the rest is lower than this, right? So this is the most serious places that we have to think about the cooling, right? How to reduce the amount of heat transfer. But when you look at the locations, right, the exhaust valve location, the spark plug location, and the piston face location, you found out that all of these places are very difficult to do the cooling. Right? It's very difficult to do the cooling. Right? It's not permits us to do the heat transfer, to do the cooling. Right? If we want to use the water jet, we cannot do it properly, right, due to the locations in here. Right? We know that all these places need to have a good heat transfer so that the temperature will not go too high. But look at the locations, it's very difficult. Right? Apart from the location problem that happen from all of these places here, right? Another problem is the time. Right? Time for us to do this kind of thing, to control the heat transfer. Time is also a matter. right? Because when you look at here, right, in overall, we have just about 60 seconds, right, before the temperature in every part of the engine, right, goes steady, right? At the beginning, it's low, of course, but when the engine start to operate, the temperature getting up for all of the spark plug, the exhaust valve, the piston, and the coolant, right? And after that, it will reach the steady temperatures. It will not go beyond this. It will not go beyond this. It not keep going on and on or up and up, right? It will stop at one certain steady temperature here, right? So our job is what? Our job is not reducing this, but our job is to reduce this. Right? This is where we have to consider, right? Because after that, our engine will experience this amount of temperature, right? As long as our engine is operating, right? As long as our engine operates. Okay. So look at the time we have. It's just only 60 seconds, right? So we have to do whatever we have if we want to reduce this temperature, right? This magnitude of temperature, we have to do it within 60 seconds, right? So it's too fast, too fast. We have, hello ปิดเสียงหน่อยครับปิดไมค์หน่อยครับโอ้โหปิดไมค์หน่อยครับฮัลโหลโอเคอ่ะยังมีตามมาอีกอ่ะโอเค so we have very few time to reduce the magnitude of these steady state temperatures, right? Very short time to do this. So it's a problem. Okay, apart from the location problem, and also we have the time problem here. Okay, so look at the heat transfer in various locations. Okay, look at the intake system. Right. The intake manifold that show about 60 degrees Celsius, right? In this picture, about 60 degrees Celsius, 60. When you look at the temperature 60 degrees Celsius, right, is of course higher than the air fuel mixture temperatures, right? It's hotter than the air fuel mixture temperature. Why the intake manifold have this high temperature? Because it's close to the engine components, right? The location of the intake manifold is close to the engine component that is hot, right? Or it's because of the design of the manifold itself, right? That would like this manifold to have a temperature higher than the air fuel mixtures, right? So the intake manifold, due to its higher temperature, can help heating the air fuel mixtures, right? So the mixtures can be easily vaporized once it enters the combustion chamber, right? So in here, we intend to have the heat transfer from the intake manifold to the air fuel mixture, right? So it easily vaporized, right? So it can well mix. Okay. So in this, to doing this, one design is to put the intake manifold in close proximity with other hot components, right? So that it will be heated. I mean, the intake manifold itself can be heated through the convective heat transfer. Just put it close to the hot components and let the convection mode do that heat transfer to the intake manifold, and then the intake manifold do the heat transfer to the air fuel mixtures. Okay. Another design is to heat the manifold directly, right? Not only depend on the convective heat transfer mode, right? This way what they do is they heat the intake manifold directly using what? Electricity or the hot coolants, right? To heat the manifold. Okay. After the manifold is heated, right, the air fuel mixture that flow into the manifold, intake manifold, is heated as well through the convective heat transfer, and the amount of heat that transfer can be calculated from this equation. Right? H stands for the convective heat transfer coefficients. A is the surface area. It has to be inside surface area of the intake manifolds. Right? And we have the temperature of the wall. Right? Wall here I mean the intake manifold wall, and the temperature of the air fuel mixture. Right? So the amount of heat that transfer from the intake manifold to the air fuel mixture can be calculated based on this. Right? It is the convective amount of heat transfer. Right? So as we mentioned, right, heat helps the fuel to vaporize faster. Right? And since it vaporizes faster, right, there is more time for the air and fuel to mix together. So it helps providing a homogeneous mixtures. Right? So this homogeneous mixture will be ready for combustion in the combustion chambers. The second location is the heat transfer in the combustion chamber. Right? The heat transfer in the combustion chamber or in the cylinder, right, it involves all three modes of the heat transfer, which are what? Conductions, convections, and radiations. Right? So all of these three modes here play an important role in the heat transfer characteristic for the combustion process. So let's look at where the heat transfer happens, okay, in the combustion chamber. Okay, the first one is happen during the intake stroke, right? Because in combustion chamber we have the intake stroke here, right? In the intake stroke, the air fuel mix is cooler than the cylinder wall, right? The air fuel mixture when it entering the cylinder inside the combustion chamber, right, is cooler than the cylinder wall. So we have heat transfer from the wall to the mixtures, and this heat will help vaporize all the fuel. Right? Apart from the intake manifold that help already, we have more help from the heat transfer, right? Where this heat come out from the wall, right, to vaporize all the fuel here. Right? And because of the fuel vaporizations that draw the heat from the cylinder wall, so the wall itself get what we call the evaporative cooling, right? That the evaporative cooling, and this will lower the amount of heat in the compression stroke, right? The heat due to compressions, right? Some of that heat will transfer out from the mixtures, right, to the wall, right? And in addition, right, the cylinder wall is also cooled down because there is the heat from the wall to the air mixture, and the fuel mixture is vaporized. So this is what we mentioned earlier. So the heat transfer in the combustion chamber during the intake stroke, right, is that we have the heat from the wall to the mixtures because the wall temperature is high. It just finished the exhaust stroke, right? And then come with the intake stroke. So the wall temperature is high. We have heat transfer to the fuel mixture, and due to that, we have the evaporative cooling. Right? And this evaporative cooling make the wall cool down. Right? The wall cool down also. Okay. Second, right, we have after compression stroke. The heat transfer that happened after compression stroke and during combustion. This time, combustion happened. So everything inside the combustion chamber have a high temperature. So now this time, we have the heat transfer from inside of the combustion chamber or from the hot gases in the combustion chamber go out to the surroundings via the cylinder wall, right? So the cylinder wall that just cool down, right, due to evaporative cooling become overheat again because of the combustions, right? So you can see the temperature of the wall go up and down, right? So the only way that we can cool down the cylinder wall in order to keep the wall from melting because of the temperature that increase due to the hot gas inside, right? We have to use conductions and then followed by convections, right? You can see in this picture, right? This is the hot gas after combustions, right? So we have high temperature here, high heat here, and we do have heat transfer through the cylinder wall. This is the cylinder wall or the combustion chamber, right? So the heat that have to be carried out through the wall, right, is have to go through the conductive heat transfer. CN stand for conductive heat transfer or conductions, right? And after the heat go to the far end of the wall here, right? It have to go out. How it go out? It need the convective heat transfer to let it to go out from the wall, right? So we are talking about the same amount of heat. No matter we talking about the heat due to conductions or the heat due to convection, they are the same amount of heat. And apart from that, it's also the same amount of heat inside here that flow to the wall, right? In which we have conductions and radiation. Okay, this is about the heat that transfer to the wall. Okay, so inside the wall here we have what? The temperature of the wall on the gas side, right? Which is the inside wall temperatures. And we also have the outside wall temperature, right? Which is the temperature of the coolant. Outside here, we have the water jacket, the water flow, our coolant flow, right? So on the outer side of the wall here, right, we have the temperature equal to the temperature of the coolant here, okay? And inside, we have the temperature of the gas, right? So T bar G here represent the average temperature of the gas here, right? And also T bar C here represent the average of the coolant temperatures. Okay. So this is what happened, right? How the heat is transferred here through conductions and then through convections. Okay. So this convective heat transfer here, QCV here that we mentioned here, right, is then carried out by either the coolant of waters or the air, right? Either carried out by this, right? For the air that the cool engine use, right? If our engine use the air to cool down, right? This engine need to have a fin. Right? The fin show right here. The coolant is on this side. Okay, the fin. If we use the air to cool down, right? Okay, so we need a fin here. But for the cool engine that use the coolant, we need a water jacket on this side. Okay. Okay. So that means the material for the combustion chamber have to be able to do this job, to do the heat transfer job, right? It have to be able to do this well enough, right? So the material requirement for the wall have to be what? It have to be a high conductivity. It have to be low density, high specific heat, high thermal diffusivity, high thermal energies, right? High thermal energy. So look at the thermal property of the wall material here. We have cast iron, aluminum, we have reactor bond, silicon nitride, space, zirconia. Right? All of these are considered to be the material for our wall. And you can see that the most appropriate one is the aluminum. When you look at the property show right here, right? Because it have high thermal conductivity, right? It have low density, it have high specific heat compared with other. It have high thermal diffusivity compared with other. It have high thermal energy compared with others. Okay, the rest is not property. Okay, so aluminum is usually used for the combustion chambers or the cylinder. Okay, another heat that we can talk is the overall heat transfer. Right? That means when we talk about the heat overall heat transfer, right? We don't want to talk about the conduction heat transfer or the convective heat transfer one by one. We don't talk about this heat one by one. Right? We want to talk about these two heat in one time. Right? And that's why we have the overall heat transfer here. Right? And this is per unit surface area of the wall, where the overall heat transfer will represent by this Q per unit area here. So it becomes small q dot here, can be calculated from here, from this expression. Right? We have the temperature of the gas, we have temperature of the coolant, and these two temperature divided by what? 1 over H sub G, which is the convection heat transfer coefficients on the gas side, and H sub C on the coolant side. Right? We have delta X here, which represent the thickness of the combustion chamber. Right? And we have K, represent the thermal conductivity of the cylinder wall. Okay, so this is the overall. If we want to talk about the heat transfer by using just one term, right? Instead of talking one by one from conduction and then to convections. Okay. How about the heat transfer on the gas side, right? We did in here. In here, right? We have convection and radiation, right? So on the gas side, it consists of the convection heat transfer per unit surface area, right, on the inside, which is what? Q, small q, Cv dot, which is the big Q, the total Q, due to convections divided by the area, right? And this equal to the heat transfer coefficients on the gas side times with the difference of the temperature between the gas side and the temperature of the wall, right? Here is the temperature of the coolant, because we talk about the overall. Here we talk only on the gas side, so it's the temperature of the wall, right? So involved with the temperature of the wall. Okay, so that means if you want to calculate this, you have to find the temperature of the wall. But if you want to talk about the same thing, you find the temperature of the gas and the temperature of the coolant. See, you see the difference? You see how difficult it is? You see why we have the overall heat transfer? Because in overall heat transfer, you only measure the temperature of the gas. You measure the temperature of the coolant, right? That flow in and out. Both of these flow in and out. Okay, right. But if you don't use the overall heat transfer, you have to find what? The temperature of the wall, right, in here, and also the temperature of, okay, oh, still not sure. Okay, okay. So only the temperature of the wall in here. Okay, right. Okay. So this wall temperature should not exceed 180 to 200 degrees Celsius, right? Why? Why we have to keep this wall temperature to be within this length? Because we want to make sure that our wall has a thermal stability, right? That means our structure strength of the wall still maintained. And this thermal stability have to happen to the lubrication oil, right? It have to be happen to the lubrication oil, right? And also we want to have the structure strength of the wall to be maintained. So that's the reason why the wall temperature should not go over than 180 to 200 degrees Celsius, right? If it's more than this, what happened to our lubrication oil? Remember, 250, yeah, 250, right? If our oil have temperature more than 250, it become coking. Okay. Okay. So this is why the water temperature should be kept within this length. Okay. So since this amount of heat, right, require the calculations of the heat transfer coefficients here. Right? The coefficient of heat transfer due to convections. Right? How we can come up with this heat transfer coefficients? Right? We have to make use on the Reynolds number and also on the Nusselt number. Right? This is called Nusselt number. Right? So these two numbers are used for comparing the flow and also the heat transfer characteristic. Right? Most of you heard about the Reynolds number in fluid mechanics. Now you hear about the Nusselt number because it involved with the flow of the gas, right, and also the heat transfer characteristic here, right. So these two numbers can help us to do the comparisons between the flow and the heat transfer characteristic for the different size, for the different speed, for the different geometry of the engine. Okay. The Reynolds number can be found from here. The Reynolds number where we have the mass of the air plus the mass flow rate of the fuel, times with the bore of the cylinder, and then divided by what? The piston face area and the dynamic viscosity of the gas inside the cylinder. Okay, so the Reynolds number found from these expressions. How about the Nusselt number? The Nusselt number is inside the combustion chamber, right? The Nusselt number can be found by using the Reynolds number, right? In which the Nusselt number is the constant C1 times with the Reynolds number to the power of the constant C2. And by definitions of the Nusselt number, it is the H sub G, right? We are looking for this time with the bore of the cylinder divided by what? Thermal conductivity of the cylinder gas. Right? This is the thermal conductivity of the working fluid, not on the material. It's the thermal conductivity of the cylinder gas. Yeah. Right. So if we know the Reynolds number, we know the constant, then we can calculate the heat transfer coefficient on the gas side. Right? So that is the first heat on the gas side, the convective heat transfer. The second heat is the radiation heat transfer. Right? Again, we calculate it based on unit surface area. Right? And this radiation heat transfer happen between the cylinder gas and also the combustion chamber wall, right? And this is the expression to find out. It's a long expression because it involves with so many parameters, right? It involves with the gas temperature, the wall temperatures, the constant that we call it a Stefan-Boltzmann constant here. It also involved with the emissivity of the gas and also the emissivity of the wall. Because it's the radiation that radiates between the gas inside the cylinder and the wall of the combustion chambers, right? Apart from this, we also have F12 here, right? Which we call is the view factor between gas and wall, right? So what is the view factor? I give you the definition here, but I think in heat transfer, right, they should talk about this view factor as well. The view factor is what? It is the proportions of the radiations which leave surface 1 that strike surface 2, right? Due to the radiation, right? So it leaves surface 1, which is the gas, and strike to the surface 2, which is the wall. right? And it also have F21 that form the wall strike back to the gas surface, right? It also have this. Okay, so this is called the view factors. Okay, so the radiation heat can be calculated from here. Okay, okay. So since it involved with the temperatures and the coefficients, right, the amount of heat transfer, let's look at the behavior of these two parameters, right, during the cycles. Okay, start from, we know that the process of the combustions in the internal combustion engine is cyclic process, right? It happen on and on and on like this, right? Go into cycle. So this will make some temperatures and coefficients no longer become a constant. It changes during the cycle, such as what? The gas temperature is higher than the cylinder wall temperature during expansion stroke, right? During expansion stroke, the gas or the temperature of the gas inside is higher than the wall, right? And during compression, it's lower than the wall. Okay, so you see it difference, not constant. Right? The gas temperature itself sometimes higher, sometimes lower, right? But when you look at the coolant temperature, which is outside, right? This coolant temperature will be very constant, right? And if it have any change to its temperatures, or if the coolant temperature change, right, it need time, right? It have to be take a longer period of time, right, before the coolant temperature change. So usually the coolant temperature will be keep constant, okay? But the gas temperature fluctuate, okay? How about the heat transfer coefficients, right? That is the temperature of the gas and the temperature of the coolant. How about the behavior of the heat transfer coefficients, right? Especially the convective one, right? The convective heat transfer coefficient on the gas side, which is Hg, right? This H sub G, right, can be very greatly within a cycle because of what? Change in the gas motions, right? The gas moving inside the combustion chamber, the swirl of the gas while it moving, the turbulence that happen, and also the velocity that happen, right? So you never have the convective heat transfer coefficient on the gas side become a constant, right? Because it experience a lot of change inside the cycle or within the cycle, where the convective heat transfer coefficient on the coolant side, the same as the temperatures, the coolant temperature, it is fairly constant throughout the cycles, right? So inside fluctuating, outside just keep constant, keep calm, right? No matter what inside happen, outside is always try to be calm, okay? How about the material, the middleman, the middleman, okay, the material. The conductivity of the cylinder will also be fairly constant, right? The middleman, the cylinder wall, the conductivity of the cylinder wall is also constant. Because what? Because we try to keep the cylinder wall temperature to be constant, right? At an overall constant temperature. We don't allow the cylinder wall to go fluctuating, same as what happened inside the cylinder, right? Otherwise, we will experience what? Remember, the structure strength of the wall will be loose, right? We will lose the structure strength of the wall here. Okay, so we will keep the cylinder wall temperature to be constant here. Okay, so this is the problem that we face when we do the heat transfer analysis. Some fluid, the gas inside, it changes. Another fluid, which is the coolant outside, constant. The wall, constant. Okay, so the heat transfer have to happen under these conditions. Okay, so we look at how the heat transfer behave during the cycles. Right? There are heat transfer to and from the cylinder wall throughout the 4 stroke of the combustion process, right? We have heat transfer happen. Right? During the intake stroke here, the cylinder wall is hotter than the fuel. Right? So vaporization of the fuel happens due to convective heat transfer. During compression, gas become warmer than the cylinder wall. Right? So we have what? Warmer than, so we have heat transfer throughout the wall here. During expansion stroke, right, there will be a greater amount of the heat transfer from the gas go to the cylinder wall. Okay, and in the exhaust stroke, the gas cool down, right? The gas cool down, so no significant amount of the heat transfer. So this is how the heat transfer behave. Sometimes we have heat through the cylinder wall from the gas. Sometimes we have the heat from the cylinder wall to the gas. It go back and forth like this during the cycle. And imagine we don't have just only one cycle. Right? We have thousands of cycles that happen when our engine operates. So the heat go in and out all the time. And that means what? If you look at the cyclic process of the combustions, you want to try to determine the heat transfer. Right? So if we look at the same point, under this weird behavior, right, in and out, okay, if we look at one particular point, right, one particular point, and this is what happened, right, at one particular point, right, you see heat in, you see heat out, right, because it's plus minus, right. So in one particular point, you observe the amount of heat transfer. The first cycle, right, like this, the first cycle, okay, this line, the first cycle happened like this. Right? Then the second cycle come in, you see, wow, nearly the same, right? So at least we see the light, or we see some way that can ease our calculation, our analysis, because at the same point, right, the heat transfer that we measure is pretty much the same, right, on each cycle, right, at the same point, right. First cycle, they show this much heat transfer. The second cycle, they show nearly the same amount of the heat transfer. Okay, so at the same point, the behavior is the same, no matter what cycle it is. Okay, but when you look at different points, then you see how difficult it is now, right? For different points, like the one showing here, 3 points, you can see that for different locations, right, it show different amount of heat transfer. Right? It show different amount of heat transfer. Right? So you have a significant variation on the amount of heat transfer that occur among these cycles, even though it happened in the same cycle. Right? For different locations, the amount difference, but for the same location on different cycle, it's the same. Okay, so this is the heat transfer behavior during the cycles. Okay, how about the heat transfer that happened in the exhaust system? The heat transfer that happened in the exhaust system. right? In here, they show you both the Nusselt number versus the mass flow rate, right? For the exhaust, if we have the actual exhaust flow, compare with if we virtually have the exhaust steady flow, right? In terms of exhaust flow, it means it is an intermittent flow, right? Because we know our cycle, sometimes it's closed, sometimes it's open, right? For the exhaust to go out, it will not let the exhaust to go out steadily, right? So this one here, they show you two lines here. In which, right, when you look at this graph, it shows you that if you look at the exhaust flow, right, if you do the analysis of on the heat transfer that happened in the exhaust flow, the actual one, the Nusselt number, right, is 50% higher than the steady flow, right? So for the steady flow, that in and out, in and out, in and out, right? Compare with the exhaust flow that in, close, and then open for out, and then close, out, open for in, right? And in, close, open for out, right? It happened like this, right? It's different, right? The amount of heat transfer is higher, almost 50%, right? Compare with the steady flow here, because the Nusselt number is higher than 50%, right? This is because of what? The cyclic pulsation in the exhaust. That's what I said. In, open, out, close, then out, open, in, close, something like this. Okay, so the exhaust flow will have a higher convective heat transfer coefficients, right? Because of higher Nusselt number. Yeah. Okay. Now, if you look at uh, the exhaust temperature of the SI engine in actual operations, right? You can look at it as a pseudo steady state. The word pseudo means as if, right? As if steady state. Because our cycle working so fast, right? So in and out, even though it intermittently, right? But it's as if steady state, right? So if you look at this, the exhaust temperature are generally in the length of what? 400 to 600, right? With the extreme length that can go as low as 300 to 900 degrees Celsius, right? This is the SI engine, right? The amount of temperature give us the sense of the amount of heat transfer that go out with the exhaust. That's why they mention about the temperature in here. Okay, so even though we try to operate the engine as fast as possible in order to get this exhaust flow to be closer and closer to the steady state flow here, right? That's what they mention, pseudo steady state here, right? Try to operate the engine at higher speed. So the intermittent actions, right? Getting less and less and less, right? And we getting closer and closer to the steady state, right? So that the amount of heat transfer to the exhaust is lower, right? Because we are getting closer and closer to the steady state flow. But the temperature, look at this, for still 400, 600, or extreme length is 300 to 900, right? Compare with the exhaust temperature of the CI engine, right? Which is what? 200 to 500 if we go for pseudo steady state, try to operate our engine, okay? So that the exhaust flow become closer and closer to the steady state, right? For the CI engine, the temperature is still 200 and 500, okay? It's lower than the SI engines, right? But look at the number, it's still You can make use of the temperature at 200, right? You can make use of the energy that's stored in the exhaust temperature that is 500 degrees Celsius. Okay. The reason why the exhaust temperature of the CI engine is lower because it had a greater expansion ratio that we mentioned in our cycle, air fuel cycle analysis, right? Okay. So look at the example. Okay. Example, calculation example. Okay. Any questions so far? Any questions so far?
Can I ask one question about
Yes.
the comparison between exhaust flow and steady flow? When you say that the exhaust flow will have higher heat transfer, it doesn't necessarily mean it is 50% higher, correct?
It's not necessary, but according to this, it's about 50% higher, right? When you compare these two lines together, it's about 50%.
I mean that, is it just a matter of increasing the convective heat transfer, or is it also like less conduction occurring?
No, we're talking about the heat that transfer with the exhaust mass, right? Because this is exhaust system. This is exhaust system, right? And since our exhaust have to flow out from our engine, right? We look at the characteristic of the flow. If we can make the exhaust flow, right? The exhaust that flow out, if we can make that flow to be steady flow. Remember, we talk about the flow. If we can make the exhaust to flow out as a steady flow, the amount of heat transfer that go out with the exhaust will be less. Compare with if we let the exhaust mass to flow out as it used to be according to the engine operations, right? The amount of heat transfer that go with the exhaust will be higher. That's the reason why they mention about this, the pseudo steady state, right? In which when we operate the engines, right? When we operate the engine, right? Even though when we look closely to our cycles, we see that our cycle sometimes close, sometimes open, sometimes close, sometimes open, right? But when we look at the engines far away, right, you will think that your engine is continuously operated. This is what they mean pseudo, right? But in fact, it's not. So we cannot fully say that our engine is operate under steady state conditions. The most we can say is that it operates under pseudo steady state. And even that, right, even though our engine, right, operate the exhaust, right, under pseudo steady state condition, the amount of the temperature, the amount of the heat transfer is still high. Look at the temperature here. That's what they want to mention to you. Right? They want to mention to you that the amount is still high with that. Compare with also the CI engine. Right? The temperature is about 200 and 500. Right? They just want to mention that even though you get a steady flow, right, the amount of heat transfer is less, right, but it's not lower as much as you expect. Okay, but if you let it go into fully exhaust flow, this is something that you have to think about, because if you let the exhaust flow to go out to be a real exhaust flow, not a steady flow, not as close to the steady flow, right? You will lose a lot of heat because of that kind of flow. This is what they want to mention. Okay, they want to indicate this. That means you just let the exhaust flow to go out as it is, you will lose a lot of heat transfer. But if you try to make the exhaust flow to flow as close as the steady flow, the amount of heat transfer will reduce. But even though you do that in our actual operations, the temperature is still this much. Okay? That means there's still some loss of the energy within the exhaust. Understand?
Yes, I understand. Thank you.
เขาให้เราดูเฉยๆว่า 50% มันลดมันสูงกว่าใช่ไหมเพราะฉะนั้นเราจะต้องพยายามดึงตัวนี้ให้ลงมานะครับซึ่งเครื่องยนต์เราจริงๆก็โอเปเรตอยู่แล้วล่ะนะครับเป็น pseudo steady อยู่แล้วล่ะแต่ขณะโอเปเรตนี่ยังประมาณ400-600เลยใช่ไหมครับนะหรือไป900นะครับนะแต่ก็ไม่เป็นไรยังดีกว่าว่าเราทำให้มันเป็น exhaust ใช่ไหมเพราะขนาดเราทำแล้วมันยังประมาณเท่านี้ถ้าเราไม่ทำอุณหภูมิมันยิ่งโดดขึ้นไปอีกถูกไหมครับนะheat transfer ก็ยิ่งมากขึ้นไปอีกนะโอเคOkay, look at the example. The exhaust manifold and the pipe leading from the engine to the characteristic converter can be approximated as 1.8 meter long pipe. Okay, so this is the exhaust manifold and the pipe leading out from the engine to the characteristic converter. This pipe is 1.8 meter long pipe with the internal diameter of 6 centimeter and outer diameter of 0.5 centimeter. So the thickness is about 0.5 centimeter. Right? The volumetric efficiency of the engine at 3,600 RPM is 93%. The four-stroke engine total displacement volume is 0.0064 cubic meter. The air-fuel ratio is 15:1, and the average wall temperature of the exhaust pipe is about 200 degrees Celsius. Okay. The temperature of the exhaust gas leaving the engine is 756 Kelvin or 483 Celsius. Okay, so this is the temperature of the exhaust gas that leave the engine. Okay, not leave the exhaust manifold and pipe. Okay, it's about 400 something, right? The average temperature, wall temperature of the exhaust pipe is 200, right? So this gives you the sense that they have a heat transfer because the gas temperature is this, the material temperature is this, right? So they have a heat transfer happen. Okay, calculate the approximate temperature of the gas entering the characteristic converter. Right? They want you to find the temperature of the gas before it gets into the characteristic converter. So the gas temperature is not at 483 degrees Celsius as it leaves the engine, right? Because the wall temperature of the exhaust pipe is only 200. So there is a heat transfer, and the result of the heat transfer is that the gas temperature will reduce. Right? They want us to find these temperatures. Okay. The density of the air at standard condition is 1.181 right? Kilometer per cubic meter per kilogram per cubic meter. Okay. The solutions procedure, how we calculate this one, right? The way to calculate this is not direct way, right? It's not direct way because we don't know the gas temperature. They ask for the gas temperature. So this problem is the trial and error problem, and it differs from the trial and error from the combustion. If you remember that trial and error, we have the equation that cover our trial and error. But this is a 100% trial and error because we have no equation that cover our trial and error process. Yeah, right. So the first step is to assume what they are looking for, right? The exhaust gas entering temperature to the characteristic converter, right? How we can assume? Have to make use of the information they given, right? The maximum temperature 483. The minimum temperature of the exhaust gas, if it could happen before entering the catalytic converter, have to be what? 200 degrees Celsius, right? It cannot go lower than 200 degrees Celsius, right? So the amount of the temperature that we assume, it have to be within this length, 483 to 200 degrees Celsius, right? So at least the information they give us help us to find the length of the exhaust gas temperatures, right, that we have to assume. Okay, so it's not just come out from nothing, right? We have some guidance to assume the exhaust gas temperature. Okay, so after we can assume the exhaust gas temperature, then we can calculate the amount of the convective heat transfer. How? Calculate the amount of the exhaust mass, calculate the flow velocity, and then find the Reynolds number, find the Nusselt number in order to find the heat transfer coefficients, and then we can calculate the convective heat transfer, right, using this equation, right? And then with this calculated heat transfer, right, we use it to calculate the difference of the temperatures of the exhaust gas. And by the difference of the exhaust gas temperature that received from this equation, we can recheck the calculate delta T here, whether it gives us the assumed exhaust gas entering temperature or not, right? If not, then we have to repeat our calculation again by assume the new exhaust gas entering temperatures. Okay, so this is how we can solve the problem. Okay, so let's first assume, right, the first approximation, right? So instead of assuming the exhaust gas temperature, we assume the delta T, right? We assume delta T is equal to 100 Kelvin. That means the entering exhaust gas temperature before the getting into the catalytic converter is about 383 degrees Celsius, right? You see, this is still higher than 200, but lower than 400. Okay, so this is our first assume, right? The air property value that we use, right? We use the approximate exhaust gas temperature here, right? So the average bulk temperature of the gas, right? We have two exhaust gas temperatures, right? Leaving the engines, which is 756, plus entering the catalytic converter that we assume 656, right? Divided by 2 here, sum of these two divided by 2, get the average bulk temperature of the exhaust gas, which is 433 degrees Celsius. We use this to find the property of the air, right? Because we assume that our exhaust is the air. So use this temperature to find other property, right, such as density, kinetic viscosity, thermal conductivity, specific heat, and also the Prandtl number. Okay, you will see later on how we use this Prandtl number. Prandtl number here. Okay. How about the mass of the exhaust gas? The mass of the exhaust gas, we can get it from the mass of the air plus fuel, right? The mass of the air plus the mass of the fuel, right? So we can make use of the mass of the air first, right? So this term expression tell us the mass of the air come out from where? The volumetric efficiency, the density of the air, the displacement volume, right? The given the speed of the engine, right? The number of crank revolutions, right? Our engine is 4-stroke or 2-stroke, right? So here is 4-stroke. So this end is 2, right? So this is the mass of the air, right? And time with what? Our air-fuel ratio is 15:1, right? 15:1. So every 1 kilogram of the fuel, we need 15 kilogram of the air, right? So 15 kilogram of the air plus 1 kilogram of the fuel becomes 16. And then we divide by 15, right? So that it means what? Every 1 kilogram of the air, this will be the total amount of mass that leave the engine, right? So we have 16 divided by 15 here, right? So the amount of the exhaust gas, right, is this, right? Because 1 kilogram of the air will have 16 divided by 15. And if we have this much amount of the air, the total mass of the exhaust will be this. Okay, get it? Here, we don't find it directly, we just find it from the ratio. Right? So every 1 kilogram of the air, we have the total exhaust equal to 16 divided by 15. Right? So if we have this much amount of the air, the total exhaust mass will be this. Okay. Then we know the exhaust mass, then we can find the average flow velocity of the exhaust, right? Through what? M dot divided by the density and the area. This area is the exhaust pipe area, right? We use the inner velocity, inside velocity, inner velocity, right? Which is 6 centimeter, okay, to calculate the cross-section area. Right? The density of the air already given, the mass of the exhaust already calculated. So the velocity of the exhaust gas inside the exhaust pipe is this 159.5 meter per second. Then we can calculate the Reynolds number for the flow in the exhaust pipe. Right? The velocity times the diameter of the pipe divided by the viscosity of the exhaust gas. Okay, come up with this. Then here, this is not they given, right? Here they use the Dituss-Brewster equations to find the Nusselt number, right? This equation based on the turbulent flow inside the pipe, right? And the equation come out like this, right? Reynolds number times with the Prandtl number, and that's the reason why we have to find out the Prandtl number, right? The Reynolds number already know, the Prandtl number already know, so we know the Nusselt number here. And through the Nusselt number, right, we know that this Dituss-Brewster equations, right, is come out from the steady flow. Usually, right, the Nusselt number equation, right, they do the experiment on the steady flow. Right? So before we apply the Nusselt number to our exhaust flow, we know that it's usually 50% higher, right? So we make use of that knowledge, right? So we time the Nusselt number that we found 272 with 1.5, right? So our Nusselt number under the exhaust flow, pulse exhaust flow, will be 408, right? 408. So we use this 408 to calculate the heat transfer coefficients, right, of the exhaust gas inside our pipe. Okay, and then when we know this, we can calculate the amount of heat transfer, right? The amount of heat transfer for the bulk temperatures, right? We did the average temperatures of the exhaust gas, right, leaving the engine and entering the characteristic converter, and the temperature of the wall, right? So this is the amount of heat that is convected from the exhaust gas to the wall pipe, okay, to the wall pipe, okay. And then this heat, right, we use this amount of heat to calculate what the temperature drop in the exhaust flow between the engine and the characteristic converter, right? And what we found is what? Delta T with the same amount of heat divided by the exhaust mass divided by Cp, right, of the exhaust, come up to be what? 117 Kelvin, right? So this heat is the convective heat between the gas and the wall, right? It is the same amount of heat that happen in the gas, right? Because it transfer from the gas to the wall, right? So the gas temperature reduce because of this, right? So we use this second equation, Q equal to mCp delta T. This talking about only the gas, right? So this delta T here is the delta T of the gas, okay? And what we found is it is 117 Kelvin. Compare with before we have what? 100, right? So it's still not quite correct. So we have to assume another exhaust gas temperature that enter the characteristic converter, right? So our new assume, right? We will use our delta T that we found, right? So the entering exhaust gas temperature to the characteristic converter will be what? 639 Kelvin, right? Not 383 as we assumed before, right? It becomes 366, right? And then we use this to go over our process again, right? Until we come up with delta T here, right? That closer to this amount. Right? It depends on how much closer you would like to have, then you can finish, right? In here, they finish at delta T equal to 112, right? And the exhaust gas temperature before entering the characteristic converter will be 371 degrees Celsius, right? Compare with when it leaves the engine, which is 483, okay? So you can see the temperature drop of about 112, right? And this temperature drop represent the amount of heat transfer from the gas through the pipe wall, right? The exhaust pipe wall. Okay. Okay. So that is the examples. Any questions on this example? Any question on this example?
I have a question.
ตอนคิดรอบหนึ่งนะครับ
อะไรนะ ฮะ
โหลครับ ได้ยินไหมครับ
ได้ยินอะไร
ค
นะ
รับ ตอนคิดรอบสองอะครับ เอาอุณหภูมิคือแบบว่าคิดใหม่ขึ้นมาเองเลยครับ
ไม่ก็นี่ไงเราก็ใช้117ที่เราหาไง
อ๋อแล้วก็ใช้อีกรอบ
ใช่แล้วก็เอาตัวเริ่มต้นตัวนี้ก็คือที่ออกจากเครื่องยนต์ไง756ใช่ไหม
ครับ
ลบแล้วนี่ก็เป็นตัวตั้งต้นใหม่ไงไม่ใช่อย่าไปแอดซูมใหม่สิถูกไหม
โอเคจะทำไปเรื่อย
ๆใช่มันก็จะคอนเวิร์ตเข้ามาเรื่อยๆให้นะโอเคครับ Okay, so the next one is the heat transfer to the engine coolant, right? The heat transfer to the engine coolant. The heat transfer to the coolant increase with higher engine speed, right? That means more and more that the increase in the engine speed, we have more and more of heat transfer to the coolant, right? This happens in order to maintain the steady state temperature, right? And the amount of heat that transfer to the coolant can be calculated according to this. We have the convective heat transfer coefficients on the coolant side, right? H sub C here, times the surface area, right? The surface area here that occupy our coolant here, right? Or the surface area of the combustion chamber with the outer surface, and this area is constant, right? And the coolant temperature, which is also constant, right? And the wall temperature here that increase with the speed, right? Okay. So this is the amount of heat that transfer to the engine coolant. Okay. How about the heat transfer in the evaporative cooling? Right. Heat transfer in the evaporative cooling. Evaporative cooling occur because our fuel is vaporized during the intakes, right? And also the start of the compressions. This evaporative cooling lower the intake temperatures, and less the intake density. Right? And that means it increased the volumetric efficiency of the engine. And since the volumetric efficiency of the engine increased, we have a better fuel consumption, right? Especially at the high speed. Okay, so this is happen naturally already, right? This heat transfer happen naturally already, right? When we operate the engines, right? In evaporative cooling. Now, if we want to increase the amount of the evaporative cooling, we can do it by inject the water, right? We add water in the intake system, right? And this water will draw the heat and evaporate. When this water evaporate, the amount of the evaporative cooling increase, right? Some engine do this, especially for the gas turbine engine, right? They inject the fuel into the intake in order to create the evaporative cooling, right? But do this, injecting the fuel into the intake system, you have to be careful because you have to avoid the corrosion problem that might happen to this engine, right? Especially when the engine are not running, because if all of the water not go into the combustion chamber, right, that means when the engine not running, right, the vaporized of this water, right, the water that is vapor inside the intake manifold will condense, right, become liquid, right, and that will create the corrosion problem. Okay, so look at the example to calculate for the evaporative cooling. Okay, we have a large supercharged aircraft, right? Engine in the aircraft normally use the benefit of the evaporative cooling more than our internal combustion engine. Okay, so the example talking about the aircraft engine, a large supercharged aircraft engine generate 900 kilowatt at 3,600 RPM when operate with air and gasoline at a fuel air equivalent ratio of 1.05. So it's a least mixture here. After supercharging and fuel additions, air enter the engine with increased temperature of 65 degrees Celsius. See, the air temperature increased due to supercharging here. Gasoline can be approximate as the isooctane CH18. Calculate how much the air is cooled by evaporative cooling when the fuel is vaporized, right? The air temperature increase, we inject the fuel mix with the air, the fuel take the heat from the air and become evaporated, right? So the air is cooled down, right? So we have evaporative cooling happen. They want to calculate how much the temperature of the air, right? They say how much the air is cool. It means how much is the temperature of the air after evaporative cooling happen. Okay, given the heat of vaporization of our fuel equal to 290 kilojoule per kilogram. Okay, this is the heat of vaporizations of our fuel. Right? The solution procedure is what? We're talking about the same heat. The heat that received by the fuel, right, equal to the heat that taken from the air, right? And this is called evaporative cooling heat. Okay, the same heat, the same amount of heat. One is received, one is given. Okay, so since we have to know the amount of the fuels, right? Because they give us only 290 kilojoule per kilogram. We have to know the amount of the fuel used. So we have to get back to our combustions. Under stoichiometric combustions, this is the fuel we use, this is the air we use, and this is the product of combustions, right? This is a stoichiometric. Then what we use is 1.05 for the equivalent air-fuel ratio, right? It's rich, less air. So the actual combustion reaction will be what? Everything here on the air side divided by 1.05, right? 1.05 here, right? And anything that we have divide on this side, such as oxygen, nitrogen, anything that involved with oxygen on the product side also have to divide by 105. Here have oxygen divided by 105. This one have no oxygen. This one have nitrogen. So it's divided by 105 also. Or you can do it directly, okay? Or recombine it, rebalancing it directly. It's okay. Either way, right? It depends on how you understanding the combustion equations, right? Okay. So when we done with this, this is our actual one, right? We can get the mass from here, right? The mass of the fuel, the mass of the air. Okay. So the heat received by the fuel is the mass of the fuel, which calculate from the number of mole of the fuel times the molecular mass of the fuel times with the heat of vaporization, right? That is given. The heat that go out from the air come out from what? The mass of the air, right? The number of mole of the air times the molecular mass of the air times with the specific heat times with the temperature difference of the air. Okay. So we know 1 kilomole, we know the molecular mass of the air, we know the heat of vaporization, the molecular mass of the fuel, we know the heat vaporization of the fuel. And this side, we know the amount of mass of the air, right? Oxygen plus nitrogen, and the molecular mass of the air, the specific heat of the air, and this delta T, right? So that means the air is cooled down by 20 degrees Celsius. So from 65, it's go down to what? 45 degrees Celsius because of the evaporative cooling, right? Okay. Another example. Now, instead of using just only its naturally evaporative cooling, now they use the water injections. They inject the water into the engine that presented in the previous examples, right? The amount of the water injected is here with 0.25 kilogram of the water injected for each kilogram of the fuel used, right? This information tells us that for every 1 kilogram of the fuel used, right, we will inject 0.25 kilogram of the water into our engine to do the evaporative cooling, right? Let the heat of vaporization of water is equal to 2,350 kilojoule per kilogram. Okay, calculate what I put here. Injected water is vaporized to do the cooling. Okay, calculate first approximate new inlet air temperature when water injection is used. Okay, apart from this, they want us to calculate also approximate new power if water injection is used, right? So not only the inlet air temperature that they want to know after they use the water injections, they also want to know the new power that received from the engine under water injections. Okay, so look at the previous information, right? Previous information, the inlet air temperature is 65 degrees Celsius, and the previous power from the engine is 900 kilowatt, right? This is, if we do nothing, let only the natural evaporative cooling happen. Okay, this is the inlet condition and the power we have from the engine. Okay, so let's first solve for the approximate new inlet air temperature, right? So for 1 mole of the fuel, the mass of the fuel will be what? 114 kilogram, right? Okay, so if you use 114 kilogram of the fuel, the mass of the water used will be what? 0.25, right? Times 114. So the mass of the water you use is 28.5 kilogram, right? Okay. The evaporative cooling from the water, which is the latent heat of the vaporization, must be equal to the amount of heat transfer from the inlet air, right? So now we have the mass of the water times the latent heat of vaporization, okay, equal to the mass of the air times Cp times delta T, right? So 28.5 kilogram, 2,350 kilojoule per kilogram, the heat of vaporization for the water equal to the mass of the air times the molecular mass times with the Cp times with delta T. So the new delta T will be what? Higher, right? 41 degrees Celsius, right? So the new entering air temperatures after water injection happen will be what? 65 minus 41, which is down to 24 degrees Celsius, right? Down to 24. It's much, much lower, right? Much, much lower. Here, that means the density will be low, right? The density will be high, not low, will be high, right? Okay. So how about the approximate new powers, right? To calculate the approximate new power, we have to go from one step to another step, keep going on, like the one I show you here, right? You start first with, you know that the fuel energies vary with the amount of mass of the fuel, right? And that means it vary with the power output, right? Because fuel energy is the source of the power output, right? Fuel energy vary with the mass, and that means what? It vary with the power output, right? But the mass of the fuel vary with the inlet mass of the air because of the air-fuel ratio, right? And that means what? That means power output, right, which depend on the mass of the fuel, vary with the inlet mass of the air, which depend on the inlet air density. Okay, and then the inlet air density vary with 1 over inlet air temperature. Right now, we can see the link, right, between the power and the information about the temperature that we have. Right, we make with what we try to do is we try to make the link between the power output with the information we have, because they just want us to find approximate new power, right? Okay, so the inlet air density vary with 1 over inlet air temperature. So that means the power output vary with 1 over the inlet air temperature. Or in other words, we can write out this equation. The power output time with the inlet air temperature become constant, right? So that means water output with water injections time the temperature, inlet temperature of the air with water injections equal to the power output without water injections time with the temperature of the air, the inlet temperature of the air without water injections, right? So this is the relationship that we can make use of the information that we have, right? We work out from one by one here until we get this. Okay, so with this, the power output with water injections equal to what? 900 times without, right? Without water injection divided by the temperature with water injection. So you can see that the power output increased from 900 to 1024 kilowatt. But this is not still our actual approximated power output. Because with water injections, some of the inlet air is depressed by water vapor, right? Because we inject the water in here. So the amount of air is not as we expect that it is, right? And this will reduce this 1024 kilowatt output. So that means we get less than this if we consider the fact that some of the inlet air is depressed by the water vapor, right? So it means what? It means we can come up with this expression, exactly the same concept that we have in here, right? The power output that includes water, right, is equal to the power output that not includes the water, right? We show right here, time with the number of mole of the air when we do not have any water, divided by the number of the air when we include the water here, right? So now what we have to find out is this number, right? So for each mole of the fuel, number of mole of the air used is what? According to our combustion equation, the actual one, right? We have to use 56.67 mole of the air, right? This is the number of mole, right, of the air that not including the water. Now, if we inject water inside, what is the number of mole of the amount of water injected? This is something that we have to calculate in terms of mole, right? We can calculate based on each mole of the fuel. That means what? We have 0.25 times 114. This is the amount of water, right? In terms of mole, it's gonna be what? 1.583 mole of water for each mole of the fuel, same as this one for each mole of the air, right? So the total number of mole for air includes water will be this. Right? So come back to our equations. Right? The power that not include the water even though we inject the water. Right? Time with the number of mole of the air when we not consider about the water that we inject, divided by the number of mole of the air when we include the water in our injections. Right? So everything in here, right, give us the water out, the power output, right, when we include the water injection into our consideration. It's going to be 996, right? So the percentage of increase in power due to water injections will be what? 10.7%. 10.7%, right? So this is, they want to calculate more clearly that here you think about the same old combustion analysis, right? But in fact, you inject the water in here, right? So the number of mole of the air is depressed by that mole of water. So you have to take that into consideration. And that means you have to come up with this relationship, right? And this relationship tells us that you have to calculate the number of mole of the air when there is no water and number of mole of the air when it includes water, right? So you have water involved with your combustion as well. And this water, right, after you use it to create the evaporative cooling, but when it gets into combustion, right, it's still some of the heat out from the combustion. That means the power output reduced. Okay, so it reduced as much to 996 kilowatt here. Okay, Okay, so that is any questions? Any questions? มีคำถามไหม
ยังไม่มีครับ
มีนะเข้าใจดีนะครับก็คิดให้ตลอดไงนะครับคิดให้ตลอดเติมน้ำใบน้ำมันไม่หายไปไหนนะ water doesn't go anywhere it's still in the engine right after that it go into combustions โอเคถ้าไม่มีคำถามนะครับโอเคอาทิตย์หน้าอยู่เดี๋ยว let me stop the recording first okay so if no question okay I will stop the recording